today what I would like to do, I give a talk about inflationary multiverse, because the word multiverse is used by many people in different ways, sometimes quite unexpected ways. Like before preparing for this lecture, I went to Google trend and check how many people are interested in multiverse, and then I found lots and lots of people, and then I checked from which country they are, and that was mainly from Thailand or somewhere else. And then I got interested, and apparently people were mostly interested in game Dragon Multiverse, something like that. So this will be different. And first of all, I need to say some words about inflationary cosmology, because this is the context in which the idea of multiverse emerged. Well, maybe not exactly that. It was a complicated game, but let's start with inflation. So this picture is just like right now many people illustrate what inflation is and how the universe expanded by showing this Big Bang point. And from this Big Bang, there is some small thing, and this small thing is written inflation, and then some time, which will different, in fact, for different versions of inflationary cosmology. And then when this stage of inflation happens, our tiny universe almost instantly becomes exponentially large. And that's why our universe is so large and so homogeneous, etc. All of these details I will describe you right now. Suppose I start in the universe with a vacuum energy V0, and what is written in the first line is the Einstein equation for expanding universe. Scale factor is given by letter A, so it's A dot divided by A is a Hubble constant, squared is proportional to energy density of the universe divided by 3. I omitted here Planck mass or gravitational constant. Planck mass is taken to be equal 1 everywhere in this talk, not to drag it everywhere in all equations. Okay, so this equation looks like that. It is H equal to A dot divided by A, proportional to the square root of this constant V0 divided by 3. So it's easy to solve, and it gives you trivial solution. A grows exponentially. That's it. It's just very easy, solvable, and give you exact answer. Now, if scale factor grows like that, then the volume grows like a cube of that. So it is like e to the degree 3 ht. And therefore the total energy, it becomes exponentially large pretty fast. And then when it decays, then the universe becomes large and it becomes homogeneous. It all produced from, well, vacuum, from nothing. It was homogeneous because of this expansion. And we have lots of particles. So this was a very beautiful idea. But unfortunately, Alan, from the very beginning, when he had written his paper, in the end, he said, there is a problem here. We do not know how to solve it. Maybe somebody will do it for us. So what was the problem? Well, I will formulate it in my own way. If something looks too good to be true, then maybe it is. So if the universe is empty, how can one tell that it expands? I mean, we assumed that it is expanding in a vacuum-like state, so how do I know that it expands? The universe with a constant positive vacuum energy is de Sitter space, it's vacuum, it looks expanding, and that's funny, and that's very unusual, and it's a general theory of relativity. It looks expanding in one system of coordinates, it looks collapsing in another system of coordinates, and static in another coordinates. So in empty space, you don't know whether it expands or not. And if there is no preferable coordinate system in the vacuum, then there is no preferable time when the vacuum state decays. And if there is no preferable time, then vacuum starts decaying whatever time it wants, and that makes the universe extremely inhomogeneous after the decay. And this decay is necessary to produce all the particles which we, well, consist of. So then it was studied for about 2 years, And both Alan Guth and Steve Hawking concluded that this scenario cannot be improved. And moreover, there was some hidden issue with this scenario. The idea was that you appeared in this vacuum state not immediately. Our universe was not born in this vacuum state. It was first hot, then it expanded, then it was supercooling, and in the state of supercooling, it emerged in this vacuum-like state. So it was pretty long time comparatively until it reaches this state of exponential expansion. But the universe could have collapsed during this time. So it was not really a full solution of all cosmological problems as we wanted to have. Everything, all units here is in units of Planckian time. In normal units, Planckian time is like 10 to the minus 43 seconds. So the universe must have survived like the first 10 to the minus 38 seconds until it started inflating, and it must be sufficiently homogeneous, etc. And also, how is that it was in a state of thermal equilibrium when it just appeared? So there were many problems which was difficult to solve in the context of this theory. Well, so a solution which was found is kind of do it halfway. So the vacuum would be not exactly vacuum state, but it will be a vacuum state with possibly some inhomogeneities, but most importantly, there is some motion potentially of the scalar field. Scalar field phi is moving with some derivative phi dot. And this turned out to be absolutely crucial. In the expression which was obtained later by those people who studied production of quantum fluctuations in an inflationary universe, a very important subject, the amplitude of density perturbations was inversely proportional to the speed of a scalar field. So if there is no scalar field, then you have extremely large inhomogeneities, and that's what was the issue. So we needed to do something else. And after several attempts, this is a scenario which I proposed in '83, and basically it was extremely simple. Suppose you study the simplest scalar field, which is just a massive scalar field. You do not even add its interaction with anything or anything. And this energy in the first approximation is just quadratic. It's like pi mesons having mass m, so they have a potential of this type. But we need a field which can be very, very large until, well, if it becomes too large, then its energy becomes larger than Planckian, then we cannot treat it classically. But if it is sufficiently large but not too large, then what happens is that when the scalar field starts falling down to the minimum, oh, by the way, why did it falling down? Why it was high in the very beginning? Well, that's why I called it chaotic inflation. It could be, the scalar field could be originally small, then the universe does not expand exponentially, and then nothing happens. It could be originally very large, then it expands exponentially, and the larger it is, the greater is the universe, so the best universes appear when this field is as large as possible. So if you study it, and let's study it, we just write two equations describing this system. The first equation is similar to what we have already written, and this A dot divided by A squared equal to this energy density of scalar field divided by 3. And another equation is a little bit unusual, equation for oscillations of a scalar field. If we ignore universe, would not have this intermediate term 3h phi dot. It would be just phi 2 dots is equal to minus m squared phi, which would be equation for harmonic oscillator. So the scalar field would oscillate just like a harmonic oscillator does. But if we add this term, and this is necessary, it's just when you solve equation for the scalar field in the expanding background, this term is necessarily appears there. This is similar then to equation of harmonic oscillator with friction. And then you know that if you have small friction, then it is harmonic oscillations. If it is very large friction, then harmonic oscillator does not oscillate, and it just slowly pendulum moves down and moves down and moves down, and that's it. Okay, so this second regime is similar to what happens during inflation, because during inflation, what happens? Look at this Klein-Gordon equation, 3h phi dot. If the speed of the field is small, then phi 2 dots is not very important term. The leading term 3h phi dot. If scalar field phi by itself, not its velocity, but the field is large, then this 3h phi dot can be very large. Oh, why it is large? Because the previous equation, h is proportional to phi. So this friction term h is proportional to phi. The larger is phi, the stronger is friction. So when the scalar field was very large, phi dot was very, very tiny, and it moved down just like this oscillator with very large viscosity. Then, when scalar field becomes smaller, Hubble constant becomes smaller, friction term becomes smaller, and then this regime ends. You will return back to this equation without this extra term. It's just oscillator. So scalar field initially, when it is large, would go down very slowly, and during this time, term m squared phi squared in the upper equation would be almost constant, and the universe therefore would expand almost exponentially. And then when scalar field gradually moved down, and then the normal oscillations start appearing, then the universe stopped its exponential expansion, and that's it. So you start with exponential expansion, and you may solve all your problems which you wanted to solve. You explain why the universe expands exponentially, why there are so many particles in it, because the total energy is exponentially large, etc. And after that, everything stops. Scalar field oscillates. Oscillations of this scalar field produce normal matter, and that will be our normal universe. So roughly speaking, this is how it looks. You may start with a universe with no particles at all, having so-called Planckian size, which is in Planckian units is equal to 1, but in normal units in centimeters, like 10 to the minus 33 centimeter. And such a universe would have mass 10 to the minus 5 gram. And it's better if it does not have any particles in it. It's okay if it has, but it's easier if its energy is just energy of a scalar field. And after that, bam, and it almost immediately, within the time like 10 to the minus 36 seconds, it becomes, yeah, this is a very large number. And it does not really matter in which units of length you use, whether it's centimeters or miles, whatever, because it is much, much greater than the size of the observable part of the universe. Let me return back here for a second. The size of the observable part of the universe is about 10 to the 28 centimeters, and this is 10 to huge amount. So it's much larger than the size of the observable part of the universe. We see just a minuscule part of the universe. And it's like living on the surface of the Earth. If the Earth would have this kind of radius, then everything would be stretched. Then the Mount Everest would become a plateau. So everything will become uniform and stuff. And everything would be very, very flat on the surface of the Earth. And that's explains why our universe right now is very flat. But then if it is our fate, it would be very bad, because how do we get galaxies? And right now we know that the universe is not exactly uniform. Without galaxies, we would not be around. So this, what happens is that quantum fluctuations produce these tiny spots in the universe, which later grow into galaxies. And this is what Planck satellite have seen in 2013. Small, tiny spots. So these small spots here, spots of temperature, is a result of development of quantum fluctuations during inflation. So origin of structure is related to this quantum fluctuation. The theory of generation of structure was first developed by Mukhanov and Chibisov in Moscow. I remember Mukhanov was sitting in a nearby office, and he told me, you know, we are explaining how galaxies are produced from quantum fluctuations. I told him, "Are you crazy? How is that?" And then what happens that it's indeed the best, and right now practically everybody accept that this is the mechanism which explains origin of inhomogeneities seeding the galaxies. So this effect can be understood as follows. All quantum fields have quantum fluctuations, the scalar field in particular. They have quantum fluctuations right now in this room on all possible wavelengths. Now, when the universe expands, this wavelength grows. And when the wavelengths of the scalar field become sufficiently large, then it becomes like almost homogeneous field, and then it is described by these equations which I've just shown. And during inflation, this homogeneous field, it does not oscillate, it freezes. So when the wavelengths of the fluctuations was tiny, then it oscillates like crazy. When it expanded, when the wavelengths grow, it suddenly stopped oscillating and frozen. And then other fluctuations, which previously were short wave, they were oscillating, and then suddenly they were frozen on the top of the previously frozen red oscillation. And then the next one, blue, which was short wave, then it was frozen on the top of this red and green oscillation. So one step after another, this is how you produce perturbations of scalar field, and these perturbations of the scalar field are responsible for perturbations of metric and perturbations of density right now in our universe. That's the mechanism of production of galaxies. So that's, first of all, let's stop here for a second, because this is insane. I remember that I was telling somebody, and this person later got Nobel Prize in cosmology. Okay, I'm telling him, explaining this is a mechanism which produce quantum fluctuations, which later produce galaxies, and he told me, no, but that's impossible, because nothing classical can be created from quantum. So it was a very, very difficult idea to swallow. Now, related to this question, which was previously not a question at all, can we see the moment of creation? And the standard answer is, oh, yes, of course. Just look at the window in a powerful telescope. When you're looking at the sun, you see what happens there like a few minutes ago. When you look at larger distance, you see galaxies created like 1 billion years after the Big Bang. Then you go closer, then you see even closer to the Big Bang. Of course, it will be more and more difficult to see. But in principle, if you have gravitational waves coming to you from the singularity, then you can see, using gravitational telescope, what happened very close to the singularity. Now, it is completely different in this new scenario. And the reason is that our universe is not of a size 10 to the 28 centimeters. It's vast, it's exponentially larger than that. And what is really closely related to all of these observations which people are right now doing, experimentally we know that the last stages of inflation ended when the energy density of the universe was about 10 orders of magnitude smaller than Planckian energy density. That's because they did not find there is a constraint on the amplitude of tensor modes produced during inflation. That's a separate issue. Do not want to go to details. The fact is that we see right now not the universe at the beginning of inflation, but only at the later stages of inflation, when inflation was already close to its end. The last 60 e-foldings that they call of inflation. E-folding is the time which is necessary for the universe to expand e times. So we see only the end of it, and we do not see the beginning. And everything that is at the beginning is at this insane distance, 10 to the whatever number, depending on the model, but typically in most of the inflationary models, it's much larger than the observable part of the universe. So we just cannot see with all of this data right now, with constraints on this parameter R, we know that last stage of inflation ended not at the Planckian density, but at density like a billion, 10 billion times smaller than that. So we see only the end of inflation, not the Big Bang. The Big Bang is something at energy of the order of 1 in Planckian units. And that's kind of, well, sad in the sense that we wanted to know, to see how the universe was born. And previously we thought that that's easy, just have a better telescope. But right now, no, we are not even close to that. Okay, so we cannot see the moment of creation, but also this means that from the practical perspective, we do not need to know what exactly happens near the Planckian density at the moment when the universe was born, because all processes which form the nearby part of the universe, actually the whole global structure of the universe, have been formed well after that, like 10 orders of magnitude in density after the Big Bang. So that's kind of protection, if you wish. It's similar to something which is called cosmic censorship conjecture, so which says that singularity may exist, but for example, if it is in black hole, the singularity is hidden from us by the black hole. In this case, singularity is hidden to us from the cosmological horizon of exponential expansion at the present moment and the previous stage of exponential expansion. So no, we cannot see the Big Bang. Okay, so this is about the basic theory. And what is the relation to the multiverse or anything? Because the main goal of inflation was to explain why the universe is everywhere the same, why it is so uniform, so homogeneous, why it does not rotate, why it's so isotropic. And now we know a solution. And this solution was kind of very similar to what Einstein wanted. He had written something in his autobiographical notes in 94, which I liked really to read, because it's really important part of how science was working all the time since that time and before that time. He said, I would like to state a theorem, and that's interesting how Einstein was writing it, a theorem which at present cannot be based upon anything more than a faith. I think it's important. We will return to this later. In the simplicity, intelligibility of nature, there are no arbitrary constants. That to say, nature is so constituted that it's possible logically to lay down such strongly determined Essentially, what he said, that our universe is given to us in one copy, and all other copies are just impossible. We have one law of physics, we have one choice of parameters of elementary particle physics. And then he said that this is great if it is so, but it is based on nothing but my faith. So let's see what happened. As I just said, main goal of inflationary cosmology was explain why at least some of Einstein's dream is right, because we see that our universe to the right of us and to the left of us at large, huge distances, it has approximately the same density, same structure of galaxies, same mass of the electron and the same mass of a proton everywhere. So we thought that we are explaining exactly this. And it turns out that this is not exactly the case. And to explain what happened, see, I'm trying to make my talk like partially, it may at some moment become hard equations, but partially the main issue with development of inflationary cosmology was not its complicated nature. As you have seen, equations are extremely trivial. Perturbations are technically a more complicated story, but equations describing inflation is extremely trivial. What was difficult, it's something psychological, because right now we do not need to say anything about hot Big Bang. We do not need it. We don't need to say anything about universe being in a thermal equilibrium from the very beginning. We do not need to assume that inflation started as an intermediate stage. We just say it started, and this was the Big Bang. Okay, so we needed to break some rules which still exist in most of the textbooks on cosmology for college, at least. They always describe inflation even as intermediate stage with some reheating and separation of forces, etc. This version of inflation doesn't exist for already 40 years, but somehow the authors of the books still live 40 years ago, perhaps. Well, so therefore there are some conceptual issues here, limits of classical cosmology. By observing, and that's something about Big Bang story as well. Big Bang story was based on the assumption, and I'm just making a movie of the universe. When looking back in time, I'm closer to the Big Bang, and then I can see how it expands right now, and I can play the movie back. If I play the movie back, and you really can't do it, then you come closer and closer to the singularity. And like, for example, you have galaxies, and when you play the movie back, you see galaxies moving closer and closer to each other, and then there are more and more particles, and that's not what happened according to inflationary theory. According to inflationary theory, when particles were produced in the process of reheating after inflation, there was no particles before. There was no galaxies. If you play the movie back, if you study evolution of the universe right now, take zoom at all galaxies and play this movie back, you will see that this movie show you that these galaxies disappear, because closer to the Big Bang you had only this vacuum state. And this does not have any easy explanation. And the reason for this mess is that this is not how it happened. All galaxies appeared quantum mechanically. And here some, old story which is in quantum mechanics serves like training for those who study quantum mechanics, some famous paradox, Schrödinger cat. So you have a cat, and the cat sits in the box, and there's some poison in the box, and depending on some quantum experiment which made there, either this poison drops on his foot and the cat dies, or not. And this is a probabilistic story. But quantum mechanics tells you that if you start with a wave function describing all future of the cat, wave function must always contain these two branches, cat which is dead and cat which is alive. And the fight about interpretation of quantum mechanics goes about 100 years. You can read about it in Wikipedia, and each author consider another one fool. The probably most closer to what we are using right now is many-world interpretation of quantum mechanics. But what we are doing right now is a little bit even more complicated, because what is the story about Schrödinger cat? You had a Schrödinger cat, and then you somehow think about two histories, Schrödinger cat dead, and then many-world interpretation of quantum mechanics says that at the moment when it happens, you understand maybe in which of these two branches of the wave functions you yourself live, whether you live in a branch in which in your branch the cat is dead, and then actually there is another branch interpretation. Okay, so here we are. In the universe, situation is much more complicated because there was no cat. That's just striking. Because there was no galaxies, because it was only vacuum. So we have two effects. Not only the cat can be dead or alive, not only galaxies can be to the right of you or to the left of you, but there was no cat, there was no galaxies. And that's only possible because we are not talking about quantum mechanics, we are talking about quantum field theory. And in quantum field theory, the number of particles is not conserved. And moreover, in inflationary cosmology, this goes to the limit because the total energy of matter in the universe is not conserved. And that also sounds crazy because we all know that energy is conserved. This is energy conservation. This is something which we know from the school. But what happens is that when you are dealing with gravity and with the universe as a whole, there is a weird theorem which tells you that the total Hamiltonian of the whole universe, taking into account gravity and matter, is actually equal to zero. And okay, I better not go into this direction. I'm just saying that you can understand it this way or that way, but the fact is that if you have a universe with this vacuum energy, total energy of matter, it was no matter, and then suddenly the matter appears. And the appearance of matter is possible only due to quantum field theory. And in addition, only because the energy of matter can grow. So it's in the exponential expansion of the universe is an example of instability which may emerge when you have this zero total energy of matter plus gravity, and then it can split into matter of gravity and matter of energy of gravity. Oh my god, I am starting talking like an old man, which I am. Okay, so total energy, which is zero, is split into energy of matter and energy of scale factor of the universe expanding. And so one of them is negative, that's gravity, and the positive, and energy of matter may become positive, which is what it does. So it looks like instability because where do you have this? Like, for example, if something stays on the top of the hill and it may fall to the right or to the left. This is spontaneous symmetry breaking. Spontaneous symmetry breaking appears because of the instability, and this instability usually occurs exponentially. That's exactly what inflation is. It's exponential instability with respect to producing of everything from nothing. Crazy. That's interpretation, but it's useful to have this interpretation in mind. Now, there are different versions of cosmology right now. I would say that inflation is most developed from all others that I aware of, but the fact is that in all of these versions, independent of which you study, large-scale structure of the universe was formed by quantum fluctuations. So right now, all of them, those who want to describe our world, I don't know any alternative explanation of creation of large-scale structure. So we need to live with this weird universe where you can fall to the right, where you can fall to the left. And this happens not only for the scalar field, which just responsible for inflation. Usually there are many other scalar fields available, like famous scalar field axions, which is very, very light. Very light fields experience quantum fluctuations as well during inflation, and these quantum fluctuations may make the scalar axions field large or small. If they are large, after inflation, they have large energy, and they can be responsible for a large amount of dark matter. Or if they are small, and this is all due to quantum fluctuations, if they are small, then there will be a little bit of dark energy. And as a result, our universe is divided into pieces. In some of these pieces, lots of dark matter or dark energy, depending on the mass of this field. Okay, so you have a universe which is no special magic for that. It's just so simple. It's just all this scalar field, and in different parts of the universe take different values. So it is a multiverse. It's a very easy subject. There is no metaphysics there. There is no like many vacuum, but we will come to many vacuum later. And that is this illustration of this idea. So when you, in the beginning of the talk, I told you, let's look at this tiny, tiny red balloon. And this red balloon expands exponentially, and it becomes a very, very large red balloon. Okay, so now let's take a football, which has many different parts, and some of them are red, some are green, black, whatever. And then it expands exponentially. And then you get a huge balloon, and the size of the red part is 10 to the degree 1 million, and the size of blue part is 10 to the degree 2 trillion. And each of them is so large that nobody living in this blue balloon will see anything about red, because they cannot talk, because the signal travels only at a distance 10 to the 28 centimeter or so, maybe 29, whatever, but not at this huge distance. So for people who live, or whoever lives there, this universe will look like a multiverse. Somebody living in a blue universe will never know about yellow universe, will never know about black or white, whatever. So each of them will try to develop a theory which explains why his part of the world is, look, it's everything that is, and therefore we must explain why the universe is yellow. And the people who live in blue, they will try to explain why it is blue. So that's the universe, multiverse. And there are two possible outlooks on that. One is pessimist. If each part of the multiverse is huge, we will never see other parts, so it's impossible to prove that we live in the multiverse, right? Okay. And optimist almost exactly repeats the sentence. If each part of the multiverse is huge, we'll never see other parts, so it's impossible to disprove that we live in the multiverse. And Einstein said, I would rather be an optimist and a fool than a pessimist and right. So in which sense this optimist attitude is more general? Because, well, we have in our own, on our own universe, so many colors. You need to prove that our universe is multicolored, that it cannot exist in any other shape, okay? And therefore, the proof is not why universe may be multicolored, but it would be necessary to explain why universe must have only single color. So it's depending on the point of view, what you need to prove, whether you need to prove that we live in the universe or multiverse. Multiverse is more general. But as I mentioned about axions, that it's not only more general, but naturally these quantum fluctuations make the universe multicolored if you even start with a single colored. And the physics of it can be explained very easily. It's I like this analogy, drunken sailor approach to cosmology. You know that drunken sailor, if he is on a plateau, he makes some number of steps, and how far he goes away from the pub grows like a square root of the number of steps he makes. Okay, because he goes backwards, forward, backwards, forward, whatever. So eventually it's a square root of number of steps. If you study scalar field, which is very, very small, having very small mass, much smaller than Hubble constant, then in the universe it also makes small steps, and it becomes, well, further and further away from the original point from which it started. And exactly it is described by this equation. It's square root of ht. Ht is this number of refoldings, number of steps this scalar field makes. And however, if you have potential energy of the scalar field which has more than one minimum, this drunken sailor, sometimes he can jump out and fall into another gutter. And that is what may happen in the universe, which have a potential energy which have many minima. And that's in general generic situation. So if you have many scalar fields, and that's pretty generic situation in modern physics, then the potential energy may have many different minima, and then during inflation it may jump from one minimum to another, and once it jumps and expands exponentially inside each of this minimum, then the universe becomes divided in this multicolored universe, and we made computer simulations which shows this process. And this was a process for this theory. This was supersymmetric SU5 theory. It does not really matter. It was a long time ago. Weinberg studied, many people studied this supersymmetric SU5 Grand 25 theory, and they found that it has three different minima, which has exactly the same energy density. And this red minima, where symmetry is not broken, then another minimum, well, purple, whatever, where symmetry is slightly broken, and then blue minimum, SU3 cross U2 cross U1, that's our minimum. That's the place where we will have our standard model where we can live, okay? And then Weinberg paid attention to the fact that if the universe was originally hot, then the symmetry was restored in this theory, and there was only one minimum, SU5. And then when temperature drops down, these two other minima appeared, but they could not have any matter in them because our universe was originally an SU5 and it cannot jump through these high barriers. So there's a problem that our universe, according to the theory, always must sit in the state with SU5 symmetry, which is not the state where life of our type is possible. Now, when inflation comes, what happens is that you have quantum fluctuations, and quantum fluctuations can take this red ball and push it towards the SU4 cross U1, and then to SU3 cross U2 cross U1, and then back, and eventually the universe becomes divided into different pieces, and we made computer simulations of it. I called it Kandinsky universe because it's similar to the painting of famous Russian abstract painter Kandinsky. So the universe becomes divided into different pieces. Each of these pieces has different colors corresponding to these different minima here. And each of them is exponentially large. So life cannot exist in red minima because there is no electrons there. Life cannot exist in the green minima for a similar reason. And life can exist in blue minima, and that's why we are there. So finally, anthropic considerations make sense. Because previously you say, we live in this SU3 cross U2 cross U1. Oh, anthropic principle would explain it. But do we have any choice? And here you see that, yes, if you have a theory with three different minima, then you have a choice. And each of these choices potentially can have exponentially large size, but you cannot live in the red minimum. Somebody else might, but you cannot live. So you have a correlation between our properties and the properties of our universe. And there's nothing metaphysical in it. It's like ice, water, liquid water, solid water, vapor water. There are three different phases of water, but fish cannot live in solid water. So this is just the same thing, but applied to this spontaneous symmetry breaking. And if somebody insists that water all liquid, then he crushes his Titanic to a piece of ice. This is another computer simulation which shows you a piece of space which was originally red. Well, I just came from a red universe, and then there are some quantum fluctuations, and they show you how these colors change, but simultaneously the height of the potential. And sometimes, not very probable, but sometimes these scalar fields start jumping higher and higher and higher again, and the colors are not formed, no fixed near the hill. So what happens there? Actually, universe there expanding with much larger speed, and even though it seems improbable that you jump so high, but then the universe expands there so fast, then actually the main volume of the universe is close to this maxima. So that's what we called eternal inflation. You start inflation under some conditions, not always, but under some conditions, you have a process of eternal inflation, our universe becomes divided into many different pieces. Some people find themselves in the blue part of the universe, some in red, and some in green, and they cannot travel from blue to red because exponentially large distances from one to another. Even if one is managed just to being born near the boundary, the travel is not advised, because if you are living, for example, in a red SU5 universe and you jump to the blue, then all particles which are possible in SU5, they do not exist in SU3 cross U2 cross U1, so you just die there. So that's very serious. They are different. It is the same fundamental law of physics. It's supersymmetric SU5 model, but low energy physics and low energy, like smaller than 10 to the 15 GeV. Okay, low energy physics is completely different in these different parts, and this means that you may have one fundamental law of physics, but different realizations, different phases, just like phases of water. So this is like genetic code of the universe, and this genetic code may experience mutations when you have quantum fluctuations which throw you from one minimum to another. And what does it mean? Well, here is a picture of the Big Bang, yellow blob downstairs. Standard idea is that if you look at the telescope, well, okay, you do not see the Big Bang, but you see something close to it. But in fact, what you see this neck connecting you to this yellow. For example, we can live in a red balloon, and you have a neck connecting me to something yellow, but this neck is it's just wrong way of drawing pictures, because everything is expanding. I need to show the picture, so it's not really a neck. And the fact is that when the person living in the red universe look back, he look at this place where kind of thing that this red universe appeared, but it just appeared because of quantum fluctuations which appeared in a yellow universe. And these fluctuations this shows you that what you see and interpret as a Big Bang, this is a pretty big bang, creation of his red balloon, but it is not really Big Bang. Okay. So transitions from one part of the universe to another can be abrupt. For example, electrons disappear, or dimension of space may change from 3 to 9, whatever. Or they may be smooth, like in the example of axions, where the fraction of dark matter or dark energy may gradually change when you travel from one part of the universe to another, except for usually it takes you exponentially long time to travel from one such part to another. In both of these cases, we live only in some parts of the universe where we can live, and which is okay. So this is the first time when, at least I was happy with anthropic principle. When I was back in Moscow, there was only one person giving talks about anthropic principle. His name was Josef Rosenthal, and he was a friend of my parents, so I just paying respect, coming to his lectures and thinking about it, well, what the idiot. Okay. And then time goes, and you see that you can implement this principle in a way which makes sense. Okay. And nevertheless, until the year 2003, this principle was very unpopular. But something happened in 2003. And what happens is that even before that, there were some papers saying that when we study string theory, potentially it may have lots of different minima, except for usually people say that like 10 to the 1,000 different solutions. That was a people Luz Schillikens. But maybe they're unstable, did not know. There was a very interesting paper by Busov and Palchinsky, who started developing this story, Susskind, and then everything changed when it was found that it is possible, maybe, it's still not at the level of theorem, it's possible to find a stable, actually metastable solution describing vacuum in string theory. We have suggested this possibility in 2003. Kachur, Kailash, Trivedi, and I was kind of cosmology consultant. And then suddenly, Mike Douglas and others, they found that no, if you find one of these solutions, then there may be 10 to the 500 different combinations of topology, of fluxes in different dimensions, etc. And when they've written 10 to the 500, they start calculating, and then maybe it is actually 10 to the degree 1500, and then well, maybe there are infinitely many. And then some other people came and say you don't have any solutions because it's inconsistent and string theory is complicated. So we really don't know at the moment who is absolutely right. It's just very confusing. It's most complicated. Many string theorists start studying high temperature superconductivity, plasma physics, cosmology. So we don't know what does it mean, if anything. But what happened at this time in 2003, we finally had this idea that we might have a solution which describes dark energy, which is possibly this vacuum state inside this theory. And then everything becomes normal. And as I mentioned, it may be many different vacua which can correspond to these different discrete parameters, depending on fluxes, etc. And it may be also continuous set of parameters, depending on where this axion evolves and into which place should it fall and where should it stay. And yeah, that's exactly the possibilities. For example, Affleck-Dyn mechanism of baryogenesis was based on some scalar field which is defining the magnitude of CP violation which is necessary for baryon symmetry. And this is just a free field that may experience fluctuations. As a result, in the universe, you may have parts of the universe which is baryons dominated, and some parts of the universe which are anti-baryons dominated. And there is some boundary between these two. Okay, and maybe we just live near this boundary, and that's why baryon asymmetry is not so significant in our universe. So suddenly you have some weird possibilities which were previously impossible. But this would be by itself would not jump a gun. What was important is that there was this cosmological constant problem. Cosmological constant problem is why energy of vacuum in the universe, this is how it was formulated originally, why it is exactly zero. And people start proving theorems explaining why it is absolutely zero. Steve Hawking tries to do it, but it was not quite right. And then there was a series of papers, fantastically beautiful papers about baby universes, etc. And then people found that actually, yeah, no, not believable. So many attempts, nobody was able to explain why cosmological constant is zero. And then the question was, maybe it is not zero. And at that time it was kind of weird. Not many people wanted even to consider it. Well, at that time I was traveling to exile to Gorky sometimes from Moscow, and we discussed with him this problem, and then almost simultaneously we've written two different papers about two different solutions for the cosmological constant problem based on anthropic principle. And I was using something which is close to what presently people called fluxes, etc. And he suggested the possibility of different Kaluza-Klein compactifications with, a huge number of different types of compactifications. So right now, just both of these ideas, but of course in much greater developed form, they're used in modern models explaining why cosmological constant vanishes. And we, at that time in 84, we said that if cosmological constant is negative, then the universe would die. Cosmological constant is positive, then it will be different universe, continue expanding fast right now, would be no galaxies. But the part of the moral shift appeared after the fantastic paper by Steven Weinberg in 87, who made this constraint that we would not be around if cosmological constant is, say, much greater than 10 to the minus 120 of Planckian density. He did it numerical. And after that, some people start believing, but nevertheless, nobody wanted to go this way. And so this stringy landscape and then everything. And then after this discovery that, or maybe discovery, we hope that it was, that string theory vacuum has many different metastable states, string cosmologists start taking it seriously. And they are very sophisticated people. So there was an explosion of publications at that time. Anthropic this, anthropic that, and probability, and what is the probability measure and stuff. And this suddenly became, from pseudoscience, non-science, anti-science, it became a legitimate science where questions can be asked, except for they were unusual. Counting probabilities in an eternally inflating universe look very strange, because it's like you have infinitely many green areas and infinitely many blue areas. It's like you have an infinitely large box of apples and infinitely large box of oranges. You say, I take one apple, one orange, one apple, one orange, and then you say I have equal number. Or you can count them like that. One apple, two oranges, one apple, two oranges, and you can counting, and then you say, oh, there are twice as many oranges. So one should be very careful how you count. But basically, what it looks right now, the idea is this. You may have many different vacuum states, and whatever probability apples or oranges, you finally have a possibility to argue this way, that you may have many different vacua, and some of this vacua has energy, vacuum energy, much greater than 10 to the minus 120 in Planckian masses. Then we cannot live there. And some of the vacua do not have even any minima. They just continue rolling the scale field like in dark energy. So if everything just rolls right now at the high energy density, we cannot live there. Or it may be rolling at energy density which is negative. But then the universe like that, it quickly collapses. And so we also cannot live there. So we can live there only in this anthropic range. Admittedly, until we really know how to measure the probabilities, it's not really a solution, but this is a state where you see, I see obvious possibility of a solution. And in that case, I may say, okay, I need to study this probability measure more attentively. Maybe it will lead to something nonsensical. But rather than that, maybe cosmological constant problem is no longer a problem. If I have students, and previously I would ask students to try to develop some solution with the cosmological constant problem, non-anthropic. And I know many people tried and failed. I would not give my students a problem like that. And I now know that I do not have a real reason to have a headache and to waking up during the night thinking about, but I'm so worried about the cosmological constant problem, because this is pretty interesting solution for that.